Right, so we can write hybridization of bonding schemes based on Lewis structures, essentially, but then also using this idea of valence bond theory to supplement that Lewis structure and VSEPR theory. So basically, write the Lewis structure, which you need pretty much all the time, and then use VSEPR theory to predict the electron geometry. Again, you could use like AXE notation. Match that up. And then you select the correct hybridization for the interior atom based on the electron geometry. And then you could sketch the model beginning with the interior atom, orbitals. I'm not going to have you draw those because they just get too messy. But what I do want to practice here is these bonding schemes in terms of what orbitals are being used and how those line up with the structures. So xenon, tetrafluoride, XeF4. So first up, when we're doing a Lewis structure, we got xenon, minimum number of bonds with all of our fluorines. Now I need the number of valence electrons. So xenon has 8, fluorine has 7, so that's 28 plus 8, 36. 7 times 4, right? So for every fluorine, I think I saw this. A little bit hard because my Chem 20 class also had an exam last week, and they also did some Lewis structures. So I might be conflating their mistakes with yours. But if I have 4 fluorines, then I need to include all of the electrons for those fluorines. So that's 7 times 4. So this is going to be 28, 8, for a total of 36. And then when we subtract out bonding electrons, we're subtracting out from our total valence electrons the number of bonds that we did times 2, so that's 8 electrons. And now I get to place the remaining 28 electrons. So we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And I have 2 more pairs of electrons that I need to place, and where should I put them? Central atom. Typically, we'll put them off axis like that so we don't confuse them with maybe another bond between the xenon and one of the fluorines. Okay, so I guess let's talk in terms of AXE notation first, right? If we're doing VSEPR theory. So how many bonding groups do I have? Huh? 6 bonding groups? 4 bonding groups. There's a total of 6, but 6 electron groups. And then 2 lone pairs. So AX4E2. What shape is this going to be? It's basically, so if we just considered electron groups, the electron geometry would be octahedral. Where would the best place for the lone pairs be? Top and bottom. So put them on the top and bottom, which means that these 4 fluorines are actually spread out in a square, flat square, with lone pair on top and bottom. So this would be square planar. Now, in terms of bonding scheme, I guess we could talk about how many sigma bonds are there. None? None sigma bonds? 4 sigma bonds. How many pi bonds are there? None. Because I don't have any double bonds. And I didn't need to form any double bonds. So I guess we could say we got 4 sigma bonds. And then we've got those 2 lone pairs also. So really, anytime we have a bond at all, that will be 1 sigma bond. If it's a double bond, then that would be also a pi bond. Now, in terms of bonding scheme, what I want to do, instead of, I guess, writing out pictures of all of the orbitals, I want to look at, actually for xenon, let's just do it like this. Instead of, I'm not going to put the row number, but we're going to have 1 s orbital in the atomic orbitals for xenon. There's 3 p orbitals, and there's 1, 2, 3, 4, 5 d orbitals. And now xenon has how many valence electrons? 8, right? It brought 8 to the table. When it forms all of these bonds, though, that's what we'll do next. So that's 1, 2, 3, 4, 5, 6, 7, 8. Okay. So based on these orbitals in valence bond theory, how many bonds without hybridizing can xenon form? Without hybridizing, there are no half-filled orbitals. So it can't form any bonds. But clearly I'm forming 4 bonds here. So how many orbitals do I need to hybridize together to be able to get 4 half-filled orbitals? Not 8, because I only have 4 bonds. If I hybridized, wait, actually, no. Yeah, I had to double check in my head. So I take 1, 2, 3, 4, 5, 6. If I take 6 orbitals, which orbitals would I use to create 6 hybridized orbitals? How many s orbitals? 1s. How many p orbitals? All 3. Then how many d orbitals? 2. So basically I would combine these all together, sp3d2. That's a total of 6 orbitals. And then if I move these electrons now, since I created these hybrid orbitals, they're all the same energy level, according to Hund's rule, they'll spread out as much as possible. We go 1, 2, 3, 4, 5, 6. And then I have 8 electrons, so I get a 7, 8. 2 of those have to be paired. So if I did 8, that would give me 8 unpaired electrons. But in this structure, I only have 4 bonds. So I only need to hybridize 4. Or I guess we only need to hybridize 6 to get 4 unpaired electrons. Yeah, usually if we're doing double bonds, then it'd be like a p orbital that would be used for a double bond. Although hypothetically we could use a d, but this is what I'm going for though. We talk about bonding scheme. I took all of my electrons, and then the quick way to know how many orbitals you need to hybridize is how many electron groups that you have. So I had 6 electron groups, so I create 6 hybrid orbitals. 2 of those get lone pairs, the other 4 are the ones that form the bonds with the fluorines. Probably can't spend too much time on this, but let's do another one. Oh, this will be good. All right, so HCN, hydrogen cyanide. So that would be the simplest skeletal structure. And then carbon, nitrogen, hydrogen. So carbon's 4 electrons, 5 electrons for nitrogen, 1 electron for hydrogen. So 10 total electrons. And I used 4 for bonds. So that's 6 electrons that I have left over. Where do I place those 6 electrons? Start on nitrogen first. 2, 4, 6. Is that done? Nope. So carbon doesn't have enough, but I can share ones from nitrogen so that it does. And we should end up with formal charges of 0. Okay, so now take the s orbitals, we got p orbitals. Actually, carbon's so small it doesn't even have d orbitals. So again, carbon has 1, 2, 3, 4 electrons of its own. Oh, I guess we didn't talk about AXE either. How many bonding groups does carbon have? 2. Triple bond counts as 1 bonding group, even though it is 6 electrons. How many electron groups does carbon have? None. How many hybrid orbitals does this carbon have? You can use the number of bonding groups, or sorry, the number of electron groups. So how many lone pairs? So it's just the 2 bonding groups. So there should be 2 hybrid orbitals that form sigma bonds. And what would those hybrid orbitals be called? SP. So I have 2 SP orbitals. And then I still have the leftover 2 leftover p orbitals. So I'll get 1, 2, and then these leftover p orbitals So how many sigma bonds do I have? 2 sigma bonds. And those are these sp. So sigma bond. How many pi bonds? Also 2. And that's the p orbitals. They're the pi bonds.
So pi bonds are just going to be like the singular orbital.
Yeah, they'll be hybrid orbitals. Yeah, they're unhybridized p orbitals that form sigma bonds. Okay, for CO2, carbon, and then 2 oxygens, so 6 times 2, that's 4. And then we got to form some double bonds. How many hybridized orbitals will this carbon have? How many sigma bonds are there? So the double bond is 1 sigma bond and 1 pi bond. So it's going to have 2 hybrid orbitals. Those will be sp again. So 1 electron in each of those. And then I'll also have the 2 leftover p orbitals with 1 electron each. But now instead of forming a triple bond with these, one is for 1 oxygen, and the other one forms a double bond with the other oxygen. But the hybridization of the central carbon is basically the same as in the HCN. Okay. Now we get to talk about molecular orbital theory. So remember at the beginning of valence bond theory, talked about how there are like Schrodinger's equations that you can try to solve for different orbital shapes and for different molecular orbital shapes. Talked about how you could do that quantitatively. That's molecular orbital theory, but again, we're going to take it in a qualitative approach because it actually can't be solved exactly. So you use what are called trial functions, basically taking an educated guess as to what the function should be, and then using that as a starting point to try and calculate the energies. Basically, you're picking a starting point and looking for the lowest energy from that starting point. Depending on how much math you've taken, you might be... So really, what we'd like to find is a global minimum. What is the absolute lowest energy between these two things? But you can get trapped in local minimums. Just as a real quick, on a 2D graph, might look something like this. If I start my trial function here, then I might move into this local minimum. And if I move to the left or right, it's going higher in energy on either side. So I might think, oh, I found the absolute minimum. But here we can see the whole graph. If I had started over here, I'd find a different lower minimum. If I start over here, it might go even lower. So starting with a trial function is like picking a point when you can't see what the entire graph looks like, and then looking for the lowest energy from there. We're not going to do that, but that's how they do it when they're trying to solve Schrodinger's equations. These are called linear combinations of atomic orbitals. So you take the valence atomic orbitals of the atoms of the molecule and do a weighted linear sum, basically calculating these two things together, adding them together, subtracting them. It takes the valence atomic orbitals for all of the atoms in a molecule. So for 2 atoms, maybe 2 hydrogens, that could be pretty simple, relatively speaking. But bigger and bigger molecules, you start adding more and more orbitals together, and the math becomes more and more complex. But in a sense, this is probably a better way of looking at the way that molecules form, because when they come together, even with the flower diagrams that we were drawing before, those are just like orbitals that are overlapping. In reality, there's no hard boundaries on where those electrons exist. Right? There's not walls that keep them fenced into those orbitals. They just exist in the area around all of the atoms as they come together. and they flow around a lot. Man, someday I'll find that video. There's a video of what a molecule might actually look like if you could look at it. And it's very hazy and it's very wobbly because those electrons in every single part of it is always moving. So trying to take these orbitals and combine them together to calculate one large function for all of the orbitals of a molecule is probably a better approach. It's also way more complicated. Again, there's the balance between accuracy and complexity. So we ideally want the highest accuracy with the lowest complexity. And so a lot of times in this class, we're taking the lowest complexity possible and just trying to get as much accuracy out of that as possible. So a lot of times the linear combinations of atomic orbitals are delocalized, meaning that orbital is not just, say if I had some carbon atoms with some hydrogens on them, we might end up with a linear combination of atomic orbitals. Instead of maybe the s orbital, whoops, for that to be the highlighter, instead of the s orbital being here around this carbon, when we combine a bunch of orbitals, it actually exists over all of the carbons, maybe over some more than others. So our hybrid orbitals that we looked at was just like, okay, if I take this one atom and I combine some of its orbitals together, that explains the shapes that we see when we actually look at those molecules and measure bond angles. This is taking that to the next level and saying, now let's combine those all. So again, if we start with something super simple like hydrogen, so one of the molecular orbitals, when we bring those two 1s orbitals together and start combining them, would give us this shape, just a sausage of electron density. So that's our sigma orbital. And then this is a bonding orbital because remember, atoms form bonds to lower their overall energy. So there has to be a reason, an energy reason for that bond to form. When we get a bonding orbital, the two 1s orbitals come together, give us one bonding orbital, but there also has to be an anti-bonding orbital. So basically the negative version of that. So our next orbital is where we've got basically there are two orbitals out of phase. And so that's our anti-bonding orbital. So there's destructive interference happening between those opposite phases. The way noise canceling headphones work, it's canceling out the sound. So anti-bonding orbital is higher energy. So it's like we take these two orbitals and we mix them together. We get two new orbitals. Am I going to get a picture? This is what I want to show you. We get two new orbitals. We say basically, let's take one of those and make it gets to be lower in energy, but the other one has to be a lot higher in energy. So that's the trade-off. Is I take this interfering part, you can think of it as the interfering part, and I push all of the interference into a new orbital, but I put all of the constructive interference into a separate orbital. So the combination of these two atomic orbitals, two molecular orbitals, which is basically what this is. So this is the idea. Every time we're bringing these two atoms together, and we're only ever going to talk about two atoms coming together to do this, basically each type of orbital will get split into a low energy bonding and a high energy anti-bonding. Which explains why these two hydrogen atoms would ever want to come together, because by themselves, they've got their single electron in a 1s orbital. When they put those together, that goes into a lower energy orbital. Again, the whole idea that atoms come together to reduce their overall energy. There's the AC. So we can calculate bond order using these, calculated bond order before, but it was mostly for mostly for resonance structures. Here, we're basically just going to count the number of electrons in bonding orbitals, and then subtract the number of electrons in anti-bonding orbitals, so those high energy orbitals, and then divide by 2, and that gives you the bond order. So again, we're not doing any of Schrodinger's equations. We don't have to pick trial functions. We don't have to do complex calculations. We get to do whole numbers minus whole numbers divided by whole numbers. Makes it very easy. But it does have some explanatory power. There is some accuracy to this that we'll see when we look at particular molecules. Basically, if this adds up, so we've got 2 electrons in a bonding orbital. Here we have 0 in anti-bonding, but if it was 2 minus 2 divided by 2, that would be 0. So the bond order would be 0. that means that molecular orbital predicts no bond will form because it's not energetically beneficial. And there are cases where you get negative, but if it's 0 or negative, the bond will not form. Because we're essentially saying the benefit of bonding orbitals or bonding electrons cancels out, or is canceled out by electrons in antibonding orbitals. And actually, just to, oh yeah, okay. So for hydrogen, it made sense because each of them has one electron. They put their electrons together, and they both went into this sigma bonding orbital. We know helium doesn't form any bonds because it wants only 2 electrons. That gives it a duet. So if we try to bring a helium together with another helium, we get the same molecular orbitals in that we get a 1s, sigma 1s bonding, sigma star, which means antibonding. But each helium is bringing 2 electrons. So we put 2 electrons into the bonding, 2 electrons into the antibonding, and our bond order ends up being 2 minus 2 divided by 2, so 0. So this predicts no bonds are going to form between 2 helium atoms. It's because of the number of electrons. So anytime we bring something together that only has 1s electrons, we're basically just going to get these 2 orbitals. And so when we bring them together in hydrogen, 1 electron, 1 electron. So both of those electrons can go into the lower energy orbital, forming a bond. If I have too many electrons, basically, they get crowded up into the antibonding orbital, and then it ceases to become beneficial for the molecule. Another thing I want to point out, so if this is the energy here of the hydrogen by itself, actually, let's go to the other one. So helium by itself, it's 1s orbital, its energy is about here. It can go down to here by putting electrons into this bonding orbital, so decreasing energy. The antibonding orbital is an equidistant higher energy than the bonding orbital. So basically, it gets a benefit here, but then if this is full, then the average is just in the middle. It's like the average of these two is in the middle, so it's like, why would it form a bond? It's not beneficial. If anything, it's the same. So there's no reason for it to form this bond because it doesn't gain any benefit. So really what we're doing when we add these bonding orbitals together and we subtract antibonding orbitals is we're calculating where is the average energy with respect to my initial atomic orbitals. If it ends up being in the middle, it's the same. There's no reason to form a bond, so it doesn't. Or if it ends up being negative, that means it's higher in energy, which means it's even less beneficial, and we're not going to form a bond. I think you could only do that in excited states. Anyways, so what if we change things up a little bit? He plus, He2 plus. So that 1 plus charge, just like with Lewis structures, means that we're removing 1 electron. So now when I look at this, I've got my He plus ion here, forming a bond with a regular helium atom. So again, 2 atomic orbitals go in. I have to get 2 molecular orbitals out. I put 2 electrons into the bonding orbital. 1 electron goes into the antibonding. So now my bond order is 1/2. Because my average energy would be something like here. So that's a benefit, right? There's a reason to form this bond because it reduces the energy sum. And I'm not sure this is an experiment that we could do, but somebody has proven that this does exist. And so it aligns with this linear combination of atomic orbitals. Things will get slightly more complicated as we add more orbitals, but not much. So we can approximate our molecular orbitals as a linear combination of atomic orbitals, meaning that I combine atomic orbitals and I get molecular orbitals, and you're just going to, actually, I'll probably give you the forms. So as soon as we add p orbitals, things get a little bit weirder. And I'll probably give you those. But when we form these molecular orbitals, we get a lower energy orbital and a higher energy orbital. And then we fill electrons in from both of our atoms from low to high, just like we did with orbital configurations or orbital diagrams. So lowest energy first, and then you pair them up to highest energy. We're still going to follow Hund's rule. And then stable bonds require a positive bond order. Even if it's a half, that's still positive. Okay. So if we're doing H2+, I'm going to have a 1s orbital from one hydrogen and a 1s orbital from the other hydrogen. What are my molecular orbitals going to be? Those are my atomic, but what are the molecular orbitals? Yeah, so it'd be 1s, I guess it's just a sigma 1s, and then I'll have a higher energy sigma star 1s. So this hydrogen has 1 electron. How many electrons does H+ have? 0. So where do I put my 1 electron in my molecular orbitals? Down here. So what's the bond order? How many bonding electrons do I have? Just 1. So the electrons in bonding orbitals, so the ones without a star, those are bonding electrons. The one in anti-bonding orbitals, those would be anti-bonding electrons. So my bonding orbital is going to be 1 minus how many anti-bonding orbitals or electrons? 0. And then divide by 2 means I have a bond order of positive 1/2. So that's stronger or weaker than regular H2? Yeah, it's weaker. So if I have regular H2, then these are each bringing 1 electron. Oops, sigma 1s, sigma star 1s. So I put 2 electrons in there. Just section this off. So it's 2 minus 0 divided by 2 equals a bond order of positive 1. So this is actually a stronger bond than a hydrogen and H+. And that's 90% of this, is just doing that. So what happens if we have, again, homonuclear, so meaning 2 of the same type of atom. So if I've got homonuclear diatomic molecules, 2 of the same type of atom, we could do this with lithium even. So notice I'm using 2s orbitals now. We're using the valence electron still. And I'm still going to get a sigma and a sigma star, so a bonding and an anti-bonding, but now it's sigma 2s, sigma star 2s. So bond order here would be 1. 2 electrons in a bonding orbital, none in anti-bonding. If we move over to beryllium, just like helium now, each beryllium has 2 electrons in a 2s orbital. So when I combine these together, I get a bond order of 0 because I got 4 electrons that fills my bonding and my anti-bonding orbital. So we would predict from this that you're never going to see a bond between 2 beryllium atoms. Oh, so moving on from beryllium, the next element would be boron. And now we've got some p orbitals. If you remember, the p orbitals have are each on a different axis. So we're just saying here that we're picking, that's what this, we assign the internuclear axis to be the x direction, meaning we're going to use the p orbital on the x-axis. So if I draw these are already drawn in. This axis is the x-axis, so those are 2 px orbitals. And when those come together, I get a anti-bonding and a bonding orbital. Does anybody know why I'm using p orbitals now instead of the s orbitals? It has electrons in the p orbital, so we have access to that now. What about the shape of an s orbital compared to a p orbital? Yeah. So what's going to come into contact first, a p orbital or an s orbital? P orbital, right? So the p orbital sticks out farther, so that's going to be able to interact. And again, we get one version of that's bonding, another version of it that's anti-bonding. So in phase and out of phase. And then the other orbitals, we can have bonding and anti-bonding for those also, so the py. So now those are running perpendicular from each other. Again, if this is the x-axis. And then because these are side on to each other, right, perpendicular, or I guess parallel to each other, parallel to each other, those are pi bonds. So if I put electrons into those, that's representing the formation of a pi bond. And then there's anti-bonding. And then I can get the other pi bond by using pz. So again, x-axis is what it means by the internuclear axis. They're both on that line. And so then I got a bonding, which is above and below, again, another pi bond. And so when we look at p orbitals and how they interact, we got to look at both the p bond or the p orbital that forms a sigma bond, and then the two p orbitals that form pi bonds. And so we'll get a bunch of different orbitals. Now, typically, the sigma 2p is lower in energy, which makes sense because that's the one that's going head on, right? That's going to be the strongest bond if it forms. And then the pi 2p orbitals will be slightly higher in energy than that. So we would order these as the sigma 2p and then pi 2p, both bonding. And then, again, think of this as, I know it's on the other slide, but, so I've got 2p orbitals for one, 2p orbitals for the other. The sigma is the lowest in energy. It's the farthest away from the average energy here. And that means that, and then the pi bonds are not as low. And that gets reflected and mirrored on the other side. So that these, since they're not as low here, the anti-bonding orbital is also not going to be as high on the other side. So you get the pi star 2p, and then the sigma pi star. Sorry, the sigma star 2p. So that the average energy is still in the middle. And that's the typical energy ordering. Because boron, carbon, and nitrogen have a different order because they're just so unique and not like the other atoms. So you gotta remember boron, carbon, nitrogen, be careful now. BCN. They have this weird order. Normally it would be sigma, pi, sigma. So when I said I would give you like the different formats, I'll give you these and then say, all right, it's this atom and this atom, fill the electrons in basically. Now I've got a lot more orbitals to fill in, but we, again, are just filling from, depending on what the two elements that are bonding are, we still fill in from low to high, and it's still bonding minus anti-bonding divided by 2. Oh yeah, so some of the reason for this is you get increased mixing and blending of orbitals. So for boron, carbon, and nitrogen, the 2s sigma gets to be a lot lower, but the 2p is a lot higher. So it's like some hybridization. Don't need to worry too much about that though. So again, we're just looking at homonuclear. So this is like a boron, 2 borons, 2 carbons, 2 nitrogens, oxygens, fluorines, so on. And you can see that the electrons for each of these are just filling in from the bottom, and every time I move over one, I just add 2 more electrons, because each carbon has 1 more electron, so if I have 2 carbons, it's 2 more electrons. And so our bond order from boron, carbon, to nitrogen increases from 1 to 2 to 3. And so does the bond energy, and the bond length gets shorter. And then once we get to oxygen, then the bond order decreases, because now after getting to oxygen, we start putting electrons into anti-bonding orbitals. And actually, no, that was for single elements, never mind. So as I start adding more electrons in here, now instead of being added into the 2 pi bonding orbitals, or the 2p bonding orbitals, I've added them into the pi star, which is anti-bonding, which is weakening that overall bond between the two. For fluorine, I've got 2 more in there. For neon, at that point, they're not going to form a bond at all, because all of the anti-bonding orbitals cancel out the bonding orbitals. So there's no benefit. This is a video of solid oxygen. So oxygen is actually paramagnetic. It's attracted to a magnetic field because it ends up with unpaired electrons. See if this even works. Yeah, okay, so we got 2 electromagnets. This is a super low res video. You can't even see it. I think that must have been like nitrogen or something. Are we going to be able to see anything? So this big smudgy blur in the middle is oxygen getting trapped between, liquid oxygen trapped between the magnets. You can actually take solid oxygen and you can make it float above a magnet. And it will lock into, because it's a superconductor, when it's frozen, as it's falling, it generates its own magnetic field because it's traveling through that. But because it's a superconductor, there's no resistance. And so the magnetic field of the oxygen locks it in place above the magnet. Pretty cool. We saw a bunch of these. And again, I would give you these bonding orders. This is N2 plus. So one of these is the plus. The other one is just going to be nitrogen. Oh, and I guess, so this is going to be 3. So this is my 2s. These are the 2p, 2s, 2p. Now, how many valence electrons does nitrogen have? 5. So 1, 2, 3, 4, 5. Now for my other nitrogen, it's N plus. So 1 less electron, it's only got 4. So 1, 2, 3, 4. And this is going to be, this is the weird bond order. Should have spaced these out more. So this is going to be the sigma. These are the pi. Double check and make sure that I have it right. Yep. This is the pi star. This is the sigma star. And then this is the sigma star 2s, sigma 2s. I guess I should say this is 2p, 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 2p. Okay, so now when we fill in the electrons, we basically have to take all of these electrons from this N plus, all of these electrons from the other nitrogen, and we just start filling them in. So how many electrons do I need to fill in total? 9. 4, 5, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, always following Hund's rule. So if we have 2 orbitals of the same energy, we unpaired spins, or unpaired first with the same spin and then pair. All right, so how many bonding electrons do I have? 2, 4, 6, 7. So all the ones that are in the bonding orbitals, so the ones that don't have a star. Star means it's anti-bonding. So I have 7 minus how many anti-bonding? Just 2. Just these ones. So 7 minus 2 divided by 2. 2.5. So is this stronger or weaker than regular nitrogen? Well, bond order for regular nitrogen is 3. Small number is weaker. Now, is it paramagnetic or diamagnetic? Paramagnetic, because it has an unpaired electron. Just like oxygen would be. Is it? Okay. Gonna spend all my time just trying to decide if I want to keep going. Yeah, let's just talk real briefly about heteronuclear diatomic molecules, just to see what that would look like. Because when you start mixing different types of atoms, there's different possibilities for the way that these molecular orbitals can arrange. Here, we're just assuming that they combine like the oxygen, fluorine, and neon would, where we got the sigmas the lowest and the highest, and the pi bonds or the pi orbital, pi bonding orbitals are in between. But the process is the same as long as you have the molecular orbitals. Just take all of the electrons from each and fill them in. And then the bond order is determined based on the number of bonding minus the anti-bonding. It's another way to predict the bonds. And yeah, the bonding order. Again, we're making this trade-off between complexity and accuracy. This is not a very complex way to do this. And so our accuracy is limited by that fact, right? We're simplifying everything as much as possible. It can give you some idea. So we have nitrogen and oxygen. We could also do like a Lewis structure, which is going to be a little bit weird because we're going to end up with 11 electrons. Minus 2 for that bond. So 2, 4, 6, 8, 9. And then we would get something like that, but also not a third bond. And the lone pair there. And see, it gets weird because we have this one unpaired electron. So what would the bond order for this be? Yeah, 2, 4, 6, 8. 8 bonding minus 3 non-bonding divided by 2 is like 2.5. And so it ends up somewhere between a double bond and a triple bond. And again, we've got an odd number of electrons also, which is weird. If we add in a third electron, or I guess another electron, then that actually would reduce this so it would only be a double bond. If we remove an electron, then we would get a straight triple bond.
Does that affect the geometry of the molecule?
This?
Having like a hazard on that triple bond?
Does that determine the geometry or? Yeah, and I think that more than just like being able to predict what it actually is, it gives us a better insight into like how these could be somewhat incomplete, or how our idea of these electrons is incomplete in its full definition. What would actually happen here? Would we have half a bond? Or would these electrons be spending less time as a part of this bonding region and more time around the terminal atoms? It's really just an incomplete picture again. But again, complexity, accuracy.
2.5, is it push more than like a bonded electrons, or
What do you mean by does it push more or less?
so how the lone pairs push?
Oh, like this single electron?
No.
The half bond. Honestly, I think for this one, we would probably, in terms of Lewis structure, we wouldn't even show a half bond. We'd do something like this and say that nitrogen's just short one electron. I don't think that it would be more repelling, and so then give you like a lesser or greater angle on other atoms if there were other bonding groups. Is that kind of what you're talking about? How if it was trigonal planar? So if I had something that was like, I'm just going to use carbon. So let's say we got some weird configuration here and it's got a half bond here. I don't think that's going to affect this angle more or less. Yeah. Awkward amount of time left. Because the beginning of the next chapter is a lot of review.